Come with me on a journey. Let's travel to the most extreme places in the cosmos. We're going to explore objects so powerful, so dense, that they challenge our very understanding of space and time. These are black holes. They are not empty holes in the fabric of the universe. Instead, they are an incredible amount of matter squeezed into an impossibly small space. Imagine the mass of a star, many times bigger than our own sun, crushed down into a city-sized sphere. This is the essence of a black hole, a place where gravity is so strong that nothing, not even light, can escape its pull. It's a one-way trip into mystery. So what exactly is a black hole? Think of it like a waterfall in the river of space-time. As you get closer, the current gets stronger. Once you cross a certain point, the point of no return, the flow is too powerful to fight. For a black hole, this point of no return is called the event horizon. It's not a physical surface you could touch, but an invisible boundary. Cross it, and you're pulled into the center, a point of infinite density called a singularity. The laws of physics as we know them break down here. It's a place where space and time cease to exist, in ways we can comprehend. The name black hole is a bit of a misnomer, because they are not empty voids. They are full of matter, just incredibly compressed. Because light cannot escape from beyond the event horizon, we can't see them directly. It's like trying to see a black cat in a completely dark room. You can't. So how do we know they are there? We look for the effects they have on their surroundings. We see stars orbiting what looks like empty space. We see superheated gas and dust swirling around an invisible point, glowing brightly before it disappears forever. These are the cosmic breadcrumbs that lead us to these gravitational titans. Our exploration of black holes is really a story about gravity. It's a story of how the most fundamental force in the universe can create objects of such mind-bending extremity. From their theoretical conception to their confirmed existence, the journey to understand black holes has pushed the limits of human intellect and technology. It's a detective story written across the cosmos, with clues scattered among the stars. Every new discovery about them teaches us more about the universe itself, from the birth of stars to the structure of entire galaxies. The story of the black hole is the story of the universe at its most extreme. The idea of a black hole is not new. It began long before we had rockets or powerful telescopes. Let's travel back in time to 1783. A brilliant English thinker named John Michell had a radical idea. He wondered, what if a star was so massive and so compact that its gravity was strong enough to trap light? He called this theoretical object a dark star. Michell used Isaac Newton's laws of gravity and his understanding of light to reason that if you could shoot a cannonball fast enough, it could escape Earth's gravity. He then calculated that a star 500 times wider than our sun, but just as dense, would have an escape velocity greater than the speed of light. Michell's idea of a dark star was a fascinating thought experiment, but it was just that, an idea. It was largely forgotten for over a century. The story picks up again in 1915 with a name you probably know, Albert Einstein. He published his general theory of relativity, completely changing how we think about gravity. Einstein showed that gravity isn't a force pulling objects together. Instead, it's a consequence of massive objects warping or curving the fabric of space-time. Think of placing a bowling ball on a trampoline. It creates a dip that causes smaller marbles to roll towards it. That's gravity in Einstein's universe. Just a few months after Einstein published his theory, a German physicist named Karl Schwarzschild found a solution to Einstein's complex equations while serving on the front lines of World War I. His calculations described the gravitational field around a single, non-rotating sphere of mass. And they revealed something strange. If you compress that mass into a small enough radius, now called the Schwarzschild radius, the curvature of spacetime becomes infinite. This creates an event horizon, the very boundary Michell had unknowingly imagined. At the time, this was seen as a mathematical curiosity, not a real object that could exist in the universe. The term black hole itself didn't come along until much later. For decades, scientists referred to these objects as gravitationally completely collapsed objects, or frozen stars. It wasn't until 1967 that the physicist John Archibald Wheeler during a conference talk, used the catchy and evocative name black hole. The name stuck. It perfectly captured the public's imagination and the object's core nature, a dark, inescapable abyss in space. The name helped transform this abstract mathematical concept into something tangible, a cosmic monster everyone could visualize, even if no one had ever seen one. So, if black holes are invisible, how do they form, and how do we find them? The most common way a black hole is born is from the death of a massive star. Stars much larger than our sun live fast and die young. At the end of their lives, they run out of nuclear fuel. The outward pressure from fusion can no longer hold back the immense crush of their own gravity. The star collapses in on itself in a catastrophic implosion, triggering a spectacular explosion called a supernova. What's left behind can be a stellar mass black hole, typically a few times the mass of our sun, but squeezed into a tiny volume. But there's another much larger type of black hole. These are the supermassive black holes. These cosmic behemoths are millions or even billions of times the mass of our sun. We find them lurking at the centers of most large galaxies, including our own Milky Way. How they got so enormous is still one of the biggest mysteries in astronomy. Did they start small and grow over billions of years by gobbling up stars and gas? Or did they form from the direct collapse of colossal clouds of gas in the early universe? Whatever their origin, these giants act as gravitational anchors for the galaxies they inhabit. The first strong evidence for a black hole came from an object called Cygnus X1. In the 1960s, astronomers detected powerful X-rays coming from the constellation Cygnus. They traced the source to a massive blue star that was wobbling as if it were orbiting an unseen companion. By measuring the star's wobble, they calculated that its invisible partner had to be about 15 times the mass of the sun. An object that massive yet completely dark could only be one thing: a black hole. The star's material was being pulled off by the black hole's gravity, forming a superheated disk that emitted the intense X-rays we detected. And right here, in our own galactic backyard, we have another example. At the heart of the Milky Way, about 26,000 light-years from Earth, lies Sagittarius A, pronounced A star. For decades, astronomers watched stars at the galactic center whipping around an invisible point at incredible speeds. Some of them complete an orbit in just a few years, moving at a fraction of the speed of light. The only explanation for these frantic stellar orbits is a supermassive black hole with a mass of about 4 million suns. It's our galaxy's gentle giant, quietly holding things together from the center. The story of black holes is filled with mind-bending discoveries that have really pushed physics to its limits. One of the most famous breakthroughs came from the brilliant physicist Stephen Hawking in 1974. He showed that black holes are not completely black after all. Because of the strange rules of quantum mechanics near the event horizon, black holes can actually, slowly leak radiation and particles back into space. This phenomenon, now known as Hawking radiation, means that black holes can, over incredibly long timescales, actually evaporate. For a stellar mass black hole, this process takes longer than the current age of the universe. But it was a revolutionary idea that connected gravity, thermodynamics, and quantum theory in a way we hadn't seen before. Another giant leap in our ability to study black holes came in 2015. For the first time, scientists at the Laser Interferometer Gravitational Wave Observatory, or LIGO, directly detected gravitational waves. These are ripples in the fabric of space-time, predicted by Einstein a century earlier. The signal they detected was from the violent merger of two stellar mass black holes that had spiraled into each other more than 1 billion light-years away. It was, honestly, like hearing the universe speak for the first time. This discovery opened a brand new window into the cosmos, allowing us to listen to the most violent events, like the collision of black holes. But the ultimate proof, the moment the world had been waiting for, arrived in 2019. The Event Horizon Telescope, a global network of radio telescopes working together as one Earth-sized observatory, captured the first ever direct image of a black hole. The target was the supermassive black hole at the center of the galaxy Messier 87. a monster 6.5 billion times the mass of our sun. The image showed a bright, glowing ring of superheated gas circling a dark central region, the black hole's shadow. There it was, the point of no return, made visible. This monumental achievement turned a theoretical concept into a tangible, observable reality. These discoveries have, profoundly changed our view of black holes. They are not just mathematical oddities. They are active and dynamic parts of the universe. Black holes don't just sit there. They warp space-time so dramatically that they can actually affect time itself. According to Einstein's theory of relativity, time slows down in a strong gravitational field. This means that for an observer near a black hole, time would pass more slowly than for someone far away. This effect, called time dilation, is not science fiction. It's a real consequence of gravity, and it's most extreme near the event horizon of a black hole. It's easy to think of black holes as cosmic monsters, mindlessly devouring everything that comes too close. They're often portrayed as villains in science fiction, like cosmic vacuum cleaners sucking up stars and planets. But honestly, this picture isn't quite right. While their gravity is powerful up close, from a safe distance, a black hole behaves just like any other object of the same mass. If our sun were magically replaced by a black hole of the same mass, Earth and the other planets would continue to orbit it just as they do now. We wouldn't get sucked in. It would just get very, very cold and dark. In fact, black holes play a crucial and even creative role in the universe. Supermassive black holes in particular are, cosmic architects. As they feed on surrounding gas and dust, they can launch powerful jets of energy and particles that travel for thousands of light years. These jets can blow away gas from a galaxy, preventing too many new stars from forming. This process, called galactic feedback, helps regulate the growth of galaxies over cosmic time. In this way, black holes are not just destroyers, they are sculptors, helping to shape the structure and evolution of the galaxies they call home. Despite all we've learned, black holes remain some of the most mysterious objects in the universe. What happens inside the event horizon? What is the singularity at the center really like? Does it lead somewhere else to another universe, as some theories suggest? To answer these questions, we need a new theory of physics, one that can unite Einstein's theory of gravity with the strange rules of quantum mechanics. This search for a theory of everything, or quantum gravity, is one of the biggest challenges in science today, and black holes are the perfect natural laboratories to test our ideas. The story of the black hole is a testament to human curiosity. It's a journey that started with a simple question asked over 2 centuries ago and has led us to the edge of reality itself. From a dark star in the mind of Jean Michel to the first stunning photograph of an event horizon, our understanding has grown in ways our ancestors could never have imagined. But the story is far from over. With every gravitational wave we detect and every new image we capture, we peel back another layer of the mystery. The cosmos is still full of secrets, and the enigmatic nature of black holes continues to inspire us to look up and wonder.